Welcome back to another day of calculus. And today we're going to be talking about two theorems. One of them is called Fermat's theorem, and one of them is called Rolle's theorem. And we'll get into what they are and why we care about them as we go into the course. But we'll start out with some definitions. And of course, I've got explainer videos on this stuff too that I've linked to. But we'll start out with some definitions, and I want to illustrate this with some work on Desmos. Let me share a little bit. We're going to talk about the idea of what is an extreme value. So when someone says extreme value of a function, well, first of all, it has to be extreme value of a function on a particular interval. So you can't necessarily just talk about the extreme value of a function. It needs to be the extreme value on an interval. And what it means is one of two things, either an absolute minimum or an absolute maximum. And so there's official definitions on page 220 in your textbook. I don't know what utility it is for me to just sort of like, write down the same definition that's in the book on the board. But instead, I definitely want to give you some examples. So let's look at some examples. So let's look at maybe even something like, so I'm pausing to let some new students in. Okay, so let's look at something even like y equals x squared. And let's take an interval. So see if I can remember, how do you specify a domain? Let's see, brackets. That's fine, that's good. So I want to identify the absolute minimum and the absolute maximum of y equals x squared on the interval from -2 to 2. Saying please move this window away from the shared screen, but there's no window there. So Zoom is trying to play tricks on me. But you can look at this and I bet you can figure it out. So the maximum values are the largest y values. That's going to be 4. And there's two x values where 4 occurs. It occurs at the two endpoints, -2 and 2. But there's one single maximum and there's one single minimum. And what I'll note about this for you is that the minimum occurs at a place when the derivative is equal to 0, when you've got a horizontal tangent. And the maximum value happens to occur at both of those endpoints. You could take the same function, y equals x squared, and you could look at a different interval, so like -3 to 2. And now you'll have a different, if I ask you now for the absolute maximum and absolute minimum, that is to say, if I ask you for the extreme values of y equals x squared on the different interval from -3 to 2, now you're going to say, well, the extreme values, the absolute maximum is 9, and the absolute minimum, once again, is 0. So the absolute max and min can change depending upon the interval upon which you pick them. I mean, the minimum still stayed at this point 0, where you have the horizontal tangent, and the maximum still occurred at an endpoint, and there's no max or min at the other endpoint. But I'm just noting that maxima and minima, they they tend to only occur at endpoints or points where the derivative is equal to 0. And you'll see that again and again in the course. So let's take a quartic or a cubic. Let's take a quartic. So let's take 4x to the fourth plus 2x cubed minus 5x squared minus x plus 1. Let's take an interval from minus 2 x to 2. Zoom out a little bit. And oh boy. So what's the absolute maximum and minimum on this interval? You might want to take like a smaller interval so that's more visible. Looks like the maximum point is up here at 59. X equals 2, one of the endpoints like usual. What's the minimum point? To zoom in a little bit to find it. Looks like the minimum point is down here. It's at a place again where we have a horizontal tangent. Looks like the minimum point is minimum value, absolute minimum is negative 1.02. But you'll also notice, like, what about this point? So this point, it sort of looks like a maximum. This point sort of looks like a minimum, but it's not the absolute minimum. So you can also make some definitions there. So I just talked about the absolute maximum and minimum. That is to say, on the given interval, what's the very biggest number and the very smallest number. But there's also a concept of what we call a local minimum or a local maximum. And those are called local extrema. So you're a local extrema if you're a local minimum or a local maximum. What does it mean to be a local minimum? It means that you are a local minimum, like if you're here or there in the graph. You're a local minimum if there is an interval around this point, like given this point, can you find an interval around the x value such that all the values of the function, at least in that small interval, are going to be bigger than the given point, the black point there. And yeah, you can totally see that. In this case, it happens to also be an absolute minimum, so you could take the interval to be the entire, negative 2 to 2 or whatever. But for this point, well, this is not an absolute minimum, but it is a local minimum because there is this small interval about 0.68 where every point in that interval is like bigger than that black point. That's why it's a local minimum. And see, you can see the definition cleanly written out there on page 221. And correspondingly, this other point I just identified, x value negative 0.096 and y value 1.048, that's a local maximum. It's not the absolute maximum. It's not the biggest point. But on the other hand, if I look, there is a small interval about this x value, negative 0.096, like sort of mousing over it now, where in that interval, every single y value of the function is less. So it makes sense, local minimum and local maximum, because there's at least some sort of small little neighborhood, if you like, in which all the points are less than. And if you go outside the neighborhood, maybe it's no longer true because you start looking over here where it gets bigger. At least in a small area, this point's the biggest. In a small area, that point's the smallest. So that's the difference between local minimum and absolute minimum. And that's the difference between local maximum and absolute maximum, which was all the way up here. Are there any questions or comments on those particular concepts? So we've been doing a graphical exploration with some particular functions, but one interesting concept or question that comes up in calculus and that comes up in optimization is, given a function and given a closed interval, like interval from a to b, like interval from -2 to 1, like including the endpoints or whatever. So given a function in a closed interval, like what we've been looking at, is there a systematic way that we can identify the extreme values, the absolute maximum and absolute minimum? That's the question. Is there a systematic way that we can identify those extreme values other than just using this graphing software? And graphing software works well on the limited number of examples that you can use, but graphing software won't solve all your problems when you're actually working in the industry. It'll solve most of your problems, but you'll still need to know the mathematics to power it. Yeah, so that's where we're headed. And just one more definition. So this definition of a critical point, and I'm gonna, I'll do some board work in a moment, but I don't want to just write down definitions on the board. So let me actually put this one. You might think this is silly, but I'm going to put this in Notepad. So this is also on page 222, but a critical point. So given like a differentiable function f of x. So take a number in the domain, call it c. In the domain of f of x is called a critical point if the following holds. So if either the derivative at c is equal to 0 or f prime of c does not exist. So we've seen some critical points in the Desmos graph that I just showed, and I'll go back and look at them. But let's look at the definition for a second. So given a function y equals f of x, a point in the domain is called a critical point if the derivative at that point is equal to 0 or if the derivative doesn't exist. So let's look at some examples. So how does that relate to what we've been talking about with absolute, with like local minimum and maximum? So here's a question for you. Where are the critical points in this picture? So visually, can you point to the 3 critical points in the picture? Give you a moment. And actually, if anybody wants to yell out what you think the answer might be, yell it out. I realize I had you muted. So if you rude, I had you muted. So like, if anybody yelled anything out and I didn't hear it, then yell it out again. that's not exactly high-level teaching to go on Zoom and ask people a question and then mute the mute the computer. So where are the critical points? Where are the places where the derivative is equal to 0? There's 3 of them, and it's here, and it's there. And how do you know that? So when is the derivative equal to 0? It's when you have a horizontal tangent line. And so you can kind of imagine the tangent lines, but it turns out that the only way that you can have a horizontal tangent line is if you are switching from like decreasing to increasing. So like if you're at a minimum or a maximum. So it turns out that so I said that a little backwards. So it turns out that like if you are a local minimum or a local maximum, then you must be a critical point, because if you're a local minimum or a local maximum, you're switching from decreasing to increasing, and therefore you have a horizontal tangent. It is possible to have a critical point without being a maximum or a minimum. Like let's take f of x equals x cubed. Yeah, look at that. Here's a critical point. This is a place with a horizontal tangent that has where this is neither a local maximum nor a local minimum. So I want to make that clear. Like you can be a critical point, but not be a local maximum or a local minimum. But on the other hand, I'm going to prove to you in a moment that if you are a local maximum or a local minimum, then you must be a critical point. You must have a horizontal tangent. So these are the 2 examples. Then there's one more I want you to keep in mind. Like keep in mind the example of local max or local min will be critical point. Keep in mind this example that says, here's a critical point where the derivative is equal to 0, but it's not a local max or local min. And one more, let's look at f of x equals absolute value of x. X equals 0 is a critical point here because the derivative doesn't exist. And it also happens to be a minimum. But those are basically the 3 ways that you can get a critical point. Like if the derivative doesn't exist, or it just happens to be equal to 0, or if it's a local max or a min, then you know the derivative is going to be equal to 0. Okay. So those are my explanations of the definitions and playing around with some examples to help solidify it. And presumably you've watched my explanation of Fermat's theorem, but I'll still like state it and go over it kind of briefly. So here it is. I think this is the same Fermat that did Fermat's last theorem. I'm not sure. I think this, I think this is someone who like wanted to be a mathematician, but it wasn't like a socially acceptable career back then. So like he became an attorney and then did math in his spare time. So this is Fermat's theorem, but I'm not great at the history, so maybe take that with a grain of salt. And it says that if f of c is a local max or a local min, then C is a critical point. And the other thing I need to assume is, I mean, I talked about f of c, so what is f? F of x is a differentiable function. So you consider a function that's differentiable at every point and suppose that you have a local max or a local minimum, and that means that C has to be a critical point. And so we saw examples of this on Desmos, but what does it look like? Let's just do this with a, I mean, in my video I did a maximum, so let's do it here with a minimum. So let's zoom in on a piece of this graph. You know, so you've got a local minimum. Maybe here's your x-axis and y-axis, and here's a piece of the graph, and here's your point C. And this is differentiable function, so you know that f prime of C exists. And you know that by definition, f prime of C is a limit of a difference quotient. And this limit is h goes to 0 of f of C plus h. Actually, I'll use this other definition. Limit is x goes to C of f of x minus f of C. Over x minus C. And remember that a limit exists exactly when it's a limit exists exactly when the left and right hand limits exist and are equal to each other. So like the limit, for instance, as x goes to C from the left would have to be equal to the limit as x goes to C from the right in order for the limit to exist. Both sides have to agree. So that is to say, this would have to be equal to the limit as x goes to C from the left which would have to be equal to the limit as x goes to C from the right. And why does that matter? So let's look at the left-hand limit. And remember that this quantity, f of x minus f of C over x minus C, remember that's the slope of the secant line from x to C. So if you're looking at the left-hand limit, you're considering values of x that are close to C but less than C. I mean, so like over here, right? But I'll draw a value of x over here just so you can see it. But imagine that it's like really close to C. And where's the y value? So that difference quotient, f of x minus f of C over x minus C, is equal to the slope of this secant line between the 2 points, and it, you know, it extends on that way. But the thing that you'll notice is that if x is less than C, then f of x is bigger than or equal to, perhaps, bigger than or equal to f of C. That's what local minimum means. It means that there's some small interval around C such that f of C is the smallest point. F of C is less than or equal to like all the other points. And so that means that the slope of this line has to be less than or equal to 0, like as indicated in the picture. And how do you show that analytically? So like if x is less than C, then x minus C has to be less than 0. If f of x is bigger than or equal to f of C, then f of x minus f of C is bigger than or equal to 0. So if you take f of x minus f of C divided by x minus C, isn't that a non-negative number? divided by a non-positive number. So think of this as like a positive number divided by a negative number. So this difference quotient is always less than or equal to 0. I mean, I guess x minus c is always less than 0 because you're not picking x equal to c. You're picking x less than c. So that's fine. But f of x is bigger than or equal to f of c. So f of x minus f of c is bigger than or equal to 0. So this quotient, non-negative or positive, so 0 or positive divided by something definitely negative, has to be less than or equal to 0. On the other hand, if you take some x value bigger than c, like if you're looking at the right-hand limit, take some x value bigger than c, like that one. And then your difference quotient is now going to be the slope of the secant line between those 2 points. The derivative then will be equal to the limit of the slopes of the secant lines. You can see what's happening now because this secant line has a slope that's bigger than or equal to 0. Because if you're considering now a value of x that's bigger than c, so if x is bigger than c, then x minus c is bigger than 0. And so now you'll have something that's bigger than or equal to 0 divided by something that's bigger than 0, and this will be bigger than or equal to 0. So why does that show anything? It shows you that the derivative is equal to this left-hand limit, which is less than or equal to 0. So it shows you that f prime of c must be less than or equal to 0. Secondly, it shows you that f prime of c being equal to the right-hand limit must also be bigger than or equal to 0. Okay, well, what's the only number that's less than or equal to 0 and bigger than or equal to 0? That would be the number 0. So it's kind of a cool argument. So this only works when you're at a local minimum. You're exploiting the fact that since you are at a local minimum, the numerator always has to be 0 or positive. And so when you're a left-hand limit, you're going to be less than or equal to 0. When you're a right-hand limit, you'll be bigger than or equal to 0. The same argument works for a local maximum. Check out my video. What will happen is that this will just become bigger than, and that'll become less than, and you'll make the same conclusion. So if you have a differentiable function, then any local max or local minimum must occur at a critical point. In other words, it must occur at a place where you have a horizontal tangent line. And you can see, like, you can really see it, because here you've got tangent lines with negative slope converging to the horizontal tangent line. Here you've got tangent lines with positive, or secant lines, excuse me, with positive slope settling down or converging to the single tangent line with a 0 slope. So that's Fermat's theorem. Any questions or comments on that? And from this, you can make a conclusion that, again, we've already seen on Desmos. This people call the extreme value theorem extreme value theorem doesn't mean that you're going to the Costco and getting an extremely good value. No, it means it's a theorem about identifying extreme values, about identifying absolute maxima and minima. So we've just done Fermat's theorem, we've just talked about local maxima and minima. So what about absolute maximum and minimum values? So this is a theorem that deals with that. So it says the following. So suppose that f is a continuous function on a closed interval from a to b. Suppose that f is differentiable on the open interval from a to b. So that is to say, suppose that f is differentiable at every single point inside the interval. It may not be differentiable at the endpoints, doesn't matter, as long as f is continuous at the endpoints and of course at every point in between. And what this is going to say is that the extreme values of f either occur at an endpoint or at a critical point. That's what I want to say, right? That's what I want to say. So how am I going to phrase this? I'll say that if f of c is an absolute max, or min, in other words, if f of c is an extreme value, then this value must occur at an endpoint or at a critical point. So that is to say, either c is equal to a, c is equal to b, or f prime of c is equal to 0. And we've seen this with the Desmos example, because you saw me write down the quartic function on the closed interval, and you saw that like the absolute maximum was at one of the endpoints, and the absolute minimum in that example happened to be a place where you had a horizontal tangent, happened to be at a critical point. And so this theorem is going to help you. It gives you a way to calculate absolute maximums and absolute minimums. And the proof for why this is true, again, check out the video for another explanation. But here's the way it goes. So I'm going to make use of a fact that we won't prove in calculus, but you prove in a later on course in analysis. If you take any continuous function on a closed interval, then it will be true that there does exist an absolute max or an absolute min. So it will be true that both an absolute max and an absolute min exist. So we'll just take that as a fact that's given to us. So you might say, since f is, I'll use CTS for continuous on AB, and absolute max and min do exist. So how could an absolute max or a min not exist? The only way that could happen is if the function ran off to infinity or negative infinity, right? And that really can't happen if you're continuous and you're on a closed interval. There's no room for any asymptotes or anything like that. So that's where that's coming from. So we're given that a maximum and a minimum do exist. So if they both, if the max and the min both occur at the endpoints, so like f of a is the max and f of b is the minimum, or vice versa. F of b is the maximum, f of a is the minimum. So what could possibly, like, what does that mean? So what happens? Let me give you some examples. So like here's A and B. Like here's an example. Where I guess there's the minimum and there's the maximum, and they both occur at endpoints. I guess there's no problem, right? And that's built into the theorem, so that's okay, fine. So what happens? Like nothing happens. There's no contradiction. I guess what we have to worry about is what if you have a maximum or a minimum that does not happen at one of the endpoints? What if you have a maximum or a minimum that happens at the interior? We should show that f prime of c is equal to 0. So I guess I should say that if the maximum and minimum both occur at endpoints, there's no issue because that's part of the theorem. On the other hand, suppose a maximum or a minimum happens at a point that's not equal to A or B, that's not equal to one of the endpoints. What do we say then? Just for argument's sake, I used minimum last time. Let's use maximum this time. So suppose that I have a number C that's between A and B, and is an absolute maximum, then in particular it's also a local maximum, because if you're in between A and B and you're the biggest point, right? You have to be bigger than or equal to the endpoints. Then you must also be a local maximum because you now have an open interval from A to B about which you're bigger than everybody else. So for an absolute maximum that's on the interior, not at an endpoint, you also have to be a local maximum.
Yeah.
Is that a question, or is that just background noise? Okay. So if you're an absolute maximum and you're in the interior, then C is also a local maximum. Not every absolute maximum is a local maximum, but those that occur not at the endpoints are local maximum. And then by Fermat's theorem, this implies that f prime of c is equal to 0. So that was the point of Fermat's theorem. It's telling us that if you want to search for extreme values, if you want to search for if you want to search for the absolute maximum and absolute minimum of a function on a closed interval, you need only check the endpoints and find out where the derivative is equal to 0. Let's actually put that to work. And before I raise any questions or comments. So let's actually put this principle to work. So here's a typical question. I'll just use one of the examples from the book. So it says, find the extrema. Find the absolute max and minimum of f of x equals, what is it, 2x cubed minus 15x squared plus 24x plus 7 on the interval from 0 to 6. And like you can just type this into Desmos like I did before with the other function, and it'll show you everything. So you can use that to check your answer, but But the question here is, can we do it by hand? And let me show you how. So you're using this extreme values on a closed interval theorem. You know that those extreme values can only occur at the endpoints or at a place where f prime is equal to 0. So let's go ahead and list the endpoints. F of 0 is equal to 7. And f of 6 is equal to whatever it's equal to. I mean, you would plug that in using a calculator. I'm just going to check the book for the answer there. It's 43. I'm not going to take 4 minutes to plug this in and spend the time doing that. You can verify plugging in the number 6 gives you 43. The next thing we have to do is check the critical points. And we'll just look and see what's the biggest. So what are the critical points? We just need to find the values of x where f prime is equal to 0. The values of x between 0 and 6 where f prime is equal to 0. So let's check that out. Let's first just take the derivative, and I'll get 6x squared minus 30x plus 24. And let's factor out 6. Check me for any mistakes. Right? And I guess we need to find the zeros of a quadratic. So we just have to factor this. So two numbers that multiply to 4 add up to -5. The only choice is x minus 4, x minus 1. And so therefore the locations of the two critical points are going to be x equals 4 and x equals 1. And those are both in between 0 and 6. So I'll include both of them. So I need to look at f of 4 and f of 1. And I'll fill in these numbers. And whichever number is the biggest is going to be the absolute maximum. Whichever number is the smallest will be the absolute minimum. So you just plug into your equation. Again, instead of doing it right in front of you to save time, I'll just look at the values that are pre-calculated by the book. And so we're getting f of 1 is equal to 18. And we are getting f of 4 is equal to -9. And so what you are concluding here is which number is the biggest, 43, and which number is the smallest, -9. So this one is the absolute max. And this one is the absolute minimum. So given a function and an interval, where are the extreme values? They either occur at endpoints or at places where the derivative is equal to 0, critical points. What do? You find those critical points that lie in the interval. You just make a list of the endpoints and the two critical points. The maximum, since it's the maximum, has to be something on the list. Just pick the biggest, and that'll be the maximum. The minimum has to be something on the list. Pick the smallest, and that'll be the minimum. So the extreme values are 43 and -9. Any question about that process? Let me also show this to you on Desmos, because I want you to not be afraid to check your work or check your answers on the software. I mean, you still have to be able to argue and like and give an argument for why your answer is correct, but this is good for checking it. So we looked at f of x equal to 2x cubed minus 15x squared plus 24x plus 7, and we were on interval from 0 to 6. So this is the graph of the function that we were discussing. And all the way up here at 6. So we found that f of 6 equals 43 is the maximum, and indeed, there it is. And what's the minimum value? I mean, if you look at the other endpoint, f of 0, that's equal to 7. And we found that out too. That was on our list, but that's not the minimum. The minimum is actually all the way down here at 4, -9. And we did correctly identify that as the absolute minimum. So when you're looking at the extreme values, well, you've got a local maximum up here at 118. We did find the local maximum too. That's not an extreme value. We had, for MOS, we had this extreme value theorem which says that the extreme values either happen at an endpoint or at one of the two critical points. In this case, here was the minimum at a critical point. And here was the maximum at an endpoint. Of course, this works for more than just polynomials, but polynomials give us good examples that are easy to factor and take derivatives of. Questions or comments on that? Okay. So let me close out the class with this one more theorem. We've done mostly computations, and then all of a sudden we get 3 theorems in one day. This is called Rolle's theorem. Also check out the video. It's another example of an application of Fermat's theorem. Let me check the statement so I don't mess it up. So like once again, you have, I'll use CTS for continuous. Once again, it's the same setup. You have a continuous function on the closed interval. You have a differentiable function. On the open interval, but this time you have some extra hypothesis that the endpoints are equal to each other. So in other words, like if I draw a typical example, so here's a function that starts out here and it's going to end at the same place that the same y value that it started, right? That's a typical example. And then the conclusion is that there must be a point strictly in between A and B there is a point C strictly in between A and B with f prime of C equal to 0. So, I mean, it's kind of similar to the extreme value thing. And how do you do this? Well, just like before, a continuous function on a closed interval must have a maximum and a minimum. So the maximum and minimum do exist. And I think once again, there's 2 cases. So if the max and minimum occur at the endpoints, so if the maximum would be like f of A and the minimum would be f of B and vice versa, the minimum is f of A and the maximum is f of B. If the max and min occur at the endpoints, because f of A and f of B are equal, the max and min must be equal. And the only option, if the maximum and the minimum are equal, is that the function is constant. And if that happens, f prime of x is going to be equal to 0 at every single point, not just 1. If you're a constant function, your derivative is 0 everywhere. So if the maximum and the minimum occur at the endpoints, and the endpoints are equal, that's a triviality. The only thing that can happen is you're the constant function. On the other hand, if a max or min occurs at some point C between A and B, then by Fermat's theorem, you know, that maximum or minimum must be a local max or local min. By Fermat's theorem, f prime of C is equal to 0. So using this extreme value theorem, like the extreme values, the max and the min, they either occur at the endpoints, in which case you're the constant function because the endpoints are equal, or if they occur on the interior, then those are places where your derivative is equal to 0. And there's two places here where that happens. Like this could be your point C, or up here, that could be your point C. This theorem doesn't say there's only one point. It says that there exists at least one point, call it C, strictly between A and B, with that derivative equal to 0. Another way people like to explain this is that if you draw the secant line between these 2 points, the average value of the function, you get a flat horizontal tangent. So you've got a function whose average value is whose average rate of change on that interval is equal to 0. And if the average rate of change on an interval is equal to 0, that means that there must be at least some place where the instantaneous rate of change is also equal to 0. It's another way of conceptualizing it. So I guess today's kind of a big day. What are the learning objectives? We had multiple definitions: absolute minimum, absolute maximum on an interval. We had the definition of local minimum and local maximum on the interval. Correspondingly, we had the definition of critical point. Then we learned about Rolle's theorem. We learned about Fermat's theorem, which says that a local max or a local min, then your derivative is equal to 0. We learned about the extreme value theorem and saw examples. Extreme value theorem says your absolute max and min on a closed interval either occur at the endpoints or at a critical point in the interior. And finally, we concluded with Rolle's theorem, which is a special case of the extreme value theorem. It says if the value of the function at the endpoints are equal to each other, f of b equals f of a, then there must be a point in between a and b such that f prime of c equals 0. The reasoning being that if the max and min occur at the endpoints, the function's constant and the derivative is 0 everywhere. Or if the maximum and minimum zero. So the question: what is f of x equal to before so f of x equals 0 in the proof? Right. So I'm saying that f of x is a constant. So I'm writing const for constant. So I'm just saying if the maximum and minimum occur at the endpoints, they are equal, and therefore f of x is a constant function. Cool. So any other final questions or comments? Okay, thank you, everybody. That's all for today, and I'll see you on Wednesday. Take care.